Audio synchronization test. A, E, I, O, U, and sometimes Y. Good, good, good. Everything seems to be in order. Catch you guys in about 4 minutes. Didn't forget to turn on my mic this time. Hello. Hello, everybody. Happy Friday. We'll be talking about C again during this lovely 50 minutes. We are just about done with this set of lecture slides. It's kind of interesting. I had reservations about whether the sets of slides I was designing would take an entire week to do. My feeling was that this particular set of slides would take a more than a week to do, and that might still be true. However, it might not be as well. We'll see. We'll see how far we get. At any rate, I've almost got the lecture slides for topic 3, ready to go to press. I've also been simultaneously working on writing some code to be able to do the auto-grading, because that's a thing that doesn't actually work natively with C and Jupyter. We have to do some scripting around certain things in order to get it to work. So I've been sort of seeing if I can get that working in preparation for the release of Assignment 1. But, lots of work to do, always lots of work to do. So, let's get back into what we were talking about. Last time we finished off with we introduced these ideas of increment and decrement operators. Incidentally, if any of you are wondering where the programming language C++ derives its name from, it is the ++ operator. Of course, the joke is kind of on them, because if the implication with putting ++ after the argument is that it is incremented after this argument is used, which is, so if you're defining your language to say this is a better version but only after you use it, that's maybe not exactly what they were going for, but C++ rolls off the tongue a bit better than ++C, I suppose. At any rate. So, we had talked about what those actually mean, the difference between prefix and postfix, and we had looked at a code example. So, let me just... Yeah, so when you use ++ or -, the magnitude of the change in the variable's value is always 1. You are adding 1, you are subtracting 1. That is the limit of it. So, Bitwise. Just a quick poll of chat. Have you guys learned about Bitwise operators in a class previous to this? This will affect the detail into which I go here. No? Not at all? You guys haven't done Bitwise operators even a little bit? Oh my goodness. Oh well, you guys are in for a treat! Bitwise is pretty fun. Alright. Good lord. There you go. So, how to explain? Okay. So, we all know that the values that are stored inside of variables are expressed in binary notation, right? Or in the binary system. They are sequences of 1s and 0s. Bitwise operators are actually a reasonably they're a reasonably straightforward concept once you get the idea of it. But the idea is that you are performing bit operations sequentially on each pair of bits if you are doing a binary bitwise operator, such as AND, OR, and XOR. Excuse me. And if it's a unary bitwise operation, which is 1's complement, that's basically the same thing as saying not. But the analogy is to Boolean operations. So we've got a bitwise AND, we've got a bitwise OR, and we have a bitwise XOR. We'll get to that one. Let's talk about bitwise AND. So if you have two variables, each having an underlying bit representation, bitwise AND means you compare the first 2 bits, you compare the second 2 bits, you compare the third 2 bits, and the manner in which you compare them is the same as a Boolean AND if 1 was true and 0 was false. So if both of those first bits are 1, then the first bit of the result will be 1. If either or both of those bits are 0, then that bit in the result will be 0 as well. I've got a slide here. I had a feeling that you guys might need I thought this would be a refresher, but, you know. So let's, oh my goodness, my little squiggly character didn't come through. Ah, oh, dang it. Good Lord. So this line is supposed to be, these are supposed to follow the same order that these guys do. So let's say we have some variable x, which is 8 bits long, and the bits that x is composed of is 1, 1, 1, 1, 0, 0, 0, 0. And let's imagine we have another variable y whose bit representation is 1, 1, 0, 0, 1, 1, 0, 0. Right? So when I say bit representation, you know, okay, here's another question for the chat. Have you guys done binary? Yeah, it is more or less the same as logic gates, including XOR. XOR is a logic gate as well. Have you guys done logic gates, and have you done the binary system? 2 more questions. Okay. Okay, so another way to think about this is that when you're performing bitwise AND, each number is the result if you took these voltages and put them into the corresponding into an AND gate, right? So 1 and 1 is 1, 1 and 1 is 1, 0 and 1 is 0, etc., all down the line. There you go. With respect to the bitwise OR operation, it's the same thing, but you use an OR gate in your brain, I guess. So if either x or y, that particular bit is a 1, it ends up 1 in the result. Otherwise, it's 0. Bitwise OR is used quite often for an operation called bit masking. Or, wait, no, let me think about that. No, it's AND, sorry. It's AND that you use for bit masking. So the idea is if you want to extract out only particular bits out of some variable, you write a binary number that contains the bits that you want to extract, and then you perform bitwise AND with the thing you want to extract them from. And that's called bit masking. You also have exclusive OR, which, generally speaking, doesn't see a whole lot of use. It's certainly not the most commonly used bitwise operator, but it's still useful to know what it is. So bitwise, like an XOR operation stands for exclusive OR, and it's like it gives you 1 when the two inputs are different, and 0 when they are the same. So it's essentially another way of thinking of it is that it's OR excluded the cases where AND would work. So there you go. So that's OR and XOR as bitwise operations. Let me just check to make sure we haven't lost too many people. Can I repeat that? Yeah, about XOR? Yeah. So when the two numbers are different, that means that it'll be 1. The value of XOR will be 1 for those bits. If the bits are the same, then the value will be 0 for those bits. There you go. So let's, I guess, move from the bottom up, and let's talk about left shift and right shift operations. Do I describe those? Yes. Left shift and right shift. So the idea with left shift and right shift is that you are moving the bits inside of their little frame of memory. So if you are moving the bits to the right, then if you take a look at X right at the top line, if you take the first 6, or sorry, the back 6 bits here, you'll notice that those are the front 6 bits of X being left shifted to, I think for you guys it's this way, left shifted by 2 bits, and those bits are backfilled with zeros. In the same way, if you're shifting in the other direction, you take these 4 ones and you shift them in the other direction. The thing to keep in mind is that this is a truncating operation, right? There's no wraparound. If a 1 is shifted off the out of the variable by a shift operation, it doesn't magically appear in the back of it. That's not how it works. So those are left and right shifts. In terms of like actual like mathematics, and I should say that right now we are working in big endian. So these numbers on this side are considered to be the largest, and these ones are the smallest. Most significant bit to least significant bit. So with the right shift, sorry, that's left shift. With the left shift operator, what you're doing is you are multiplying by 2 and then truncating anything that's outside of the range of bits that you're allowed for that integer. Multiplying by 2 the number of times specified. So you could think of it as being equivalent to x equals x times 2 to the power of whatever this number is. In the same way, if you're right shifting, you're performing division by 2, the number of times specified here, with truncation. So hopefully that is a sufficient description of left and right shift operations. They really do what they say on the can. And as for this guy, which is 1's complement, that one's simpler. That one falls in line with these guys because this is a binary NOT operation. So, like if you, I don't know if they call them NOT gates or inverter gates, but the idea is that zeros become 1s and 1s become zeros. You can see it's just the flipped representation. You take every bit and you flip it, and that's what the 1's complement operation does. I'm just going to check chat, see if we haven't lost too many people. My mic cut out. Uh-oh. Is there a way to do wraparound? So there's a way to do everything. You would probably have to hold some intermediate variables. Like, you'd have to store data somewhere else. The problem is that, like, what I'm describing to you when I'm describing these bitwise operations, these are CPU instructions. So, bitwise operations can be done in one operation on the CPU. If you wanted to do left shifting with wraparound, you would have to store the bits that were lost, perform, or store the bits that you were about to lose, perform the shift, and then put those bits in the correct place on the other side. You would have to do that manually. The CPU has no command for that, unless it does. CPUs have a lot of commands, or they have a lot of instructions. But yeah, so the advantage of these operations is that they can be performed very, very, very fast. These are among the fastest operations that you can ask a computer to perform, because it's just bit manipulation. There is a heck of a lot less going on with these operations than even something like addition. It might be useful for you guys to learn some, like what addition looks like on according to the bits and stuff like that. But that's kind of its own. That would be its own set of slides. Maybe not a whole set of slides, but that would be its own set of slides. Trying to think where we could squeeze that in. Well, at any rate, I will think about that and see if we can't squeeze in some stuff about how the CPU actually performs things like addition. Maybe. We'll see. We'll see. I can't make any promises. Not gate, yeah. Oh, an interesting thing you can do with live streaming, actually, is you can actually like go back 1 minute and then watch the live stream, but like 1 minute delayed. And like if I'm boring, you can fast forward again, then get back into the stream, contemporaneously. So that good question. If this is done in one CPU instruction, how does the left shift multiply by 2 and then truncate? Because the circuit just drops those wires. So the well, I don't know. It's possible that it's performing one, like left shift by 1 twice, so it might be 2 operations. But essentially, all that's happening is that if you imagine a bank of 1s and a bank of 0s, if you put X in the bottom bank and all of the wires leading from bank 1 to register 1 to register 2 are just like they go to 1 over, and then a 0 feeds into the least significant one, then that's how you would implement a left shift in circuit. So, that the wire for the last one just doesn't go anywhere. It doesn't connect up anywhere to the output register. So, hopefully that's an answer to your question. Cool. So, so that's bitwise operations. I hope that that has been informative. I'm only slightly disappointed that you guys didn't see that in 1D04. The problem with 1D04 sometimes, I think, is that it has to serve too general an audience. Bitwise operations are extremely useful. You'll find bitwise operations are extremely useful when you start doing embedded systems programming as well in 3rd year. the thing about embedded systems programming is that a lot of the time you're going to be bit whacking like this. Like when you have a microcontroller, a lot of the time, well, the inputs to a microcontroller are things like digital I/O pins and analog I/O pins. But if you think about the digital ones, that's just a high or a low voltage coming into the chip. And if you think about what output means in the context of a microcontroller, you're also again, it's a digital input-output pins. So and when I say pin, if you see one of those black boxes with the metal things coming down, those are pins. You apply voltage to those to get results, and voltage sometimes comes out of them. So when it's necessary for you to for you to send some digital output over a pin, that's going to be one bit of data. So it's useful to be able to, it's useful to know what the operations are on bits. So hopefully this will be important for you in your future. I think the next slide we probably don't have to cover in as fine a detail. Hopefully all of you know what relational and logical operators are. However, the nomenclature for logical operators, or the syntax for logical operators, has changed as opposed to Python. So equality is double equals, inequality is bang equals, greater than or equal to, less than or equal to, all very bog standard. Logical operators, not is the value prepended by the exclamation mark character, and is 2 ampersands. Now in Python you just typed the word and, but in pretty much every other frigging programming language that exists, and is double ampersands, or is double bar character. If you're looking for the bar character on your keyboard, you hit Shift and that button that's above Enter on a standard keyboard. So double bar is or, double and is and, or double ampersand is and. So that should be reasonably straightforward. I keep looking there for the chat. No, the assignment is the assignments start next week. Yeah. So this is a pun because we're talking about modified assignment statements. So you may already be familiar with things like plus equals and minus equals. In C, you actually have pretty much all of your binary operators can be used with in this sort of assignment plus syntax. You've got addition, subtraction, multiplication, division, modulo, left shift, right shift, bitwise and, bitwise or, and exclusive or. Oh, one more sort of mental connection for you. Notice that the symbol for bitwise and is just one of the symbols from logical and the same thing for bitwise or and logical or. This should be a clue as to this underlying semantics of what's going on with those. So yeah, so you've got assignments, various types of assignments, all types of assignments. You can use them as much as you like. Let me see if we have any comments. Okay. So we also have a number of keywords in C. These are things that are, for example, you're not allowed to use these as variable names or anything like that. You should not touch these. These are restricted keywords. I'm not going to read them all, but you'll notice there are things in there like int, double, goto, static struct, switch, typedef, return, for, char, case, enum, break, unsigned, void, volatile, while, all of the words that are used in the language. Basically everything but symbols and curly braces. So there you go. And there are some that have been added by subsequent standards. The C99 the C99 standard added bool, and C11, these are numbered by the year they came out, added things like no return, static assert, etc., etc. There we go. So, let's talk about if statements. Things are a bit different in C versus Python. Oh, geez. All right. I see how it is. All right. If statements are a bit different in C versus Python. For one thing, what's in an if statement is not dictated by indentation. It is dictated by the curly braces. Again, white space doesn't matter. I do still encourage everyone to follow the Python convention for indentation. The reason that Python uses that indentation scheme, semantically, is because it is the standard that was arrived at by C programmers and, programmers of other similar languages. This is a visual style that is easy to read and works. So even though, it's like writing your program all on one line. Possible, but not recommended. One important difference, if you're used to and familiar with Python's elif statements, these are replaced with else if. So you have to add those three characters in the middle. Semantically, it does the exact same thing as an elif. It's just this is the syntax for how you write it. Let me see if we have any questions. Good. So, I have a comic. Mom, can we get an if statement? No, we have an if statement at home. The if statement's at home. And this, if you know anything about programming, this should make you cringe so hard that the soles of your feet, suck into your feet and, are tickling your intestines. So, let's talk about switch cases. Python does not have switch cases. It's actually one of my biggest bugbears with Python. Personally, I find Python and its attitude towards switch cases personally annoying. I feel like they did that specifically to irritate me. But, So what is a switch case? A switch case is a construct that allows you to execute certain blocks of code based on the matching of an expression to particular literals. So we have 1, 2, and 3, x, 1, 2, and 3. We have x, so where x goes, you can put any arbitrary expression. The switch case evaluates that expression and then judges equality against all of the things that you specify as cases. So you don't have to do 1, 2, 3, and you don't have to just test integers either. These can be, anything you can test in an equality, you can use a switch case for. This construct actually has more to do with Goto statements than with if statements, but we're going to talk about Goto. That's right, folks, we're going to talk about Goto. I'm going to teach you guys the forbidden magics. So, this is how a switch case works. x is evaluated. If x is equal to whatever literal is put here, then all of the code inside of this case executes. It is typical to end a case with a break statement. If you do not have a break statement, then execution will flow through into the next case. So case 3, in this case, if x is equal to 2, then it'll do everything in here, everything inside of case 2. Then it will fall through to case 3, execute everything inside case 3, and then hit a break. The default statement executes if no case has been activated, and the default statement is optional. If you don't want the switch case to do anything in the case that no matches occur, then you just leave out the default statement. Cool. Do I have an example? I do have an example. All right. Thought I put an example in there. So, questions? So, in this example, x is the controlling expression. The value of the controlling expression is compared to each case label, which is a literal of the return type of the controlling expression. Execution jumps to the corresponding case and exits the switch block when it hits a break statement. This means that execution may pass through multiple... that's a spelling mistake. Oh, geez. Multiple cases before exiting the switch block. Default functions, like the terminating else in an if-else chain. If no case matches the value of the controlling expression, execution jumps to the default clause. So this is what that looks like visually. We start case A's actions, break, etc., etc. This is for cases that are all terminated with a break expression. So this is a program that is designed to be sarcastic to you about your grade. I believe I have that in the... We'll load her up code. Let's see. Maybe it's in topic, the slide code. Is there code here? Jeez. Yes, sarcasticgrades.c. So, obviously, we can compile. So, sarcasticgrades.c is just... It's just this file that is... this code that's split over two slides right there. There you go. We compile it with GCC. There we go. It compiles. We execute it. Sarcastic. Enter your grade. A. Amazing. A smart person. You have met expectations. So notice that it is executing both this print statement and this print statement. There's no break in between. However, if we were to follow the B branch, we just get this. Right? If we enter something that is none of the options, it says that's not even a proper grade. There you go. Oop, jeez. Let's see if we have any questions. Yes, Cameron. In the previous example, the case for 3 executes when x is equal to 2. So it's implicitly any case where there's no break, it falls through to the next one. Yeah, that's how it works. Yeah, Dennis, if that guy is gonna, I appointed mods for a reason, you guys, just so you know. The tag %C is used for character data types. So that's so I had a question: what happens if you enter F? And that's a good question. It says to you, well, they're always hiring in the Army, which is true, actually. If you ever think that the economy is too bad that you can never get a job, just keep in mind that they're always hiring in the Army. So, actually, especially if you have a sufficient amount of IQ to be able to handle an engineering degree, people like that they're especially hurting for, and they will pay to attract people like that. But anyway, a historical note on Goto statements. So I mentioned that switch cases operate seemingly in a very similar manner to something like a Goto. It's more structured than a Goto, though. And the thing about a switch case is that all of the cases have to occur inside of these curly braces, which limits the scope of the jumping around that can occur. But there is an older and more ancient form of program manipulation, which used to be the only way that you could do it, and that is the Goto statement. Gotos, you should feel trepidation and fear at the sound of Goto, because Gotos are generally a terrible way of doing things, at least in a modern context. However, I feel it's important for you guys to know about them, so I put them in the slides. So, it may blow your minds to know this, but at one point there was no such thing as an if statement. This if statements were an innovation at one point. Of course, stored program computers were at one point an innovation, so maybe that isn't so surprising. Program execution was at one point controlled using what's called a Goto statement. Goto statements change the value of the program pointer to some other point in the code. In BASIC, this was done using line numbers. And in BASIC, like old BASIC, not Visual Basic, but the language Visual Basic grew from, you had to actually manually number your lines, which is kind of interesting and cool. And at the same time, terrible in a lot of ways. Generally speaking, Goto statements made code just about impossible to read, and it is from Goto statements that the pejorative term spaghetti code is derived. The idea of spaghetti code is the reason that we call badly written code spaghetti code is if you have in your hand just a great big clump of spaghetti noodles, it's impossible to tell where one noodle ends and the next begins. And what happens to code that's written with a lot of Goto statements by an undisciplined programmer is you have these threads of execution, these possible threads of execution that go all the way around through the file all over the place, because they're often added ad hoc and not like following no particular convention, and it takes a very, very long time in order to trace the execution path of any particular thread of execution in this. And when I say thread of execution, I'm not talking about like threads in the modern sense that you'd have multiple threads running on your CPU. I'm speaking more about linear segments of code that don't branch, right? So these things were just sort of wound all around each other, and it's very, very difficult to actually figure out what's going on, and that is why spaghetti code is a term. This is also why many languages do not even include support for Goto statements. But because C is so frigging old and has to main back compatibility to programs that were written in the 70s, Goto statement. This was before Goto statements had acquired this sort of this patina of terribleness that they've acquired, like this reputation for being terrible that that they have acquired gradually over the years. So it's kind of interesting, but a if statement is actually just syntactic sugar for a few gotos. You know, where your program execution skips a segment of code if the condition is false. That skipping action itself, in the underlying CPU instructions, that is a goto statement. That is modifying the value of the program pointer. And I realize I'm probably going to have to explain what the program pointer is, because people are probably already asking about it in the chat. But let me just finish this slide, and then we'll talk about what the program pointer is. So, this means that modern program control is technically less flexible than program control that uses gotos. However, the combination of if statements and while loops, or the combination of branching statements and loop statements, they can make every possible program, every program that it's possible to express using goto statements alone can be expressed using a combination of if statements and loops. This is the concept of Turing completeness, for those computational nerds out there. So Goto may, in some cases, be able to come up with a more compact notation for what you're trying to do, but generally speaking, it's not worth the trouble of trying to read it. That's why everybody has settled on the convention that Goto statements are terrible. C has Goto statements. Their use is discouraged in the strongest possible terms. Please do not use them. However, having said please do not use them, the next slide will be about how to use them. But anyway, let me check to see if we have any chat questions. Yep. Good. Excellent. I see our white blood cells are doing their job. Do you need to know how to use Goto statements? No. This is yeah, thank you. Okay. I think everybody in the chat at some point needs to express appreciation for the moderators. Thank you, moderators. You are wonderful people. I'm glad that I appointed you, and not one of the trolls who asked to be a moderator. That would have been hilarious. Yeah. Cool. Yes. Yeah, and the other thing about trolls is the more they feed on attention. So the more attention that you give them, the more they're gonna, do what they do. So. Let's, okay. So, no, you don't need, this isn't need-to-know stuff. Well, it will be once you start doing assembly. I'm pretty sure do you guys still have a course in third year on assembly programming? Because if you do, Goto statements are actually the only, assembly doesn't have loops. It has conditionals, but you couldn't call them if statements. You have to hook them up to Goto statements manually. So, while not recommended for C, they are pretty much the only way to get around an assembly code. So, if you intend to do some assembly classes, you're going to have to learn how a Goto works anyway. So, there you go. 2. Ha! Puns. So, to use Goto statements, which you should never ever do ever in your life, unless you're programming in assembly, do the following. Number 1, create a label within your program. A label is any valid identifier followed by a colon, and that's the only thing on the line. You then create Goto statements referencing the labels. So, for example, here is an example of a program that you should absolutely not ever, ever, ever put into your computer. And this replicates the functionality of a do-while loop. So we have int n is equal to 1. This is the label. I have called it label so that you know it is a label. You then print the what n is, n++. If n is less than or equal to 10, go to label. So you just keep going through here until this condition is no longer true, and then you exit and return 0. So let's talk loops. And seems like we might actually get through all of this in the next 4 minutes. So there you go. In C, there are 3 types of loops: while, do while, and for loops. There are also 2 control statements for use inside of loops: break and continue. Hopefully this is stuff that you guys have mostly already done in Python. So, while loops in C work the same as in Python. There's no difference except for the fact that you're using curly braces now instead of indentation. Do-while loops are a slight variation. So a do-while loop, this is how you write it. You have an initializing statement, do, open the brace, put your body statements, make sure always to update whatever the variable is, and then close and do and write while, and then put your condition at the end. So a while loop tests the condition before each loop iteration. A do-while loop tests the condition after each loop iteration. This means that do-while loops must execute at least one loop iteration, whereas a while loop does not necessarily execute any of its loop iterations. Aside from that, there's no actual semantic difference with respect to while and do-while loops. It's just when you're testing the condition. So, so I have a question. In assembly programming, can we make a user-defined function named if and make it do the if statement? Possibly. I'm not sure you have functions, to be honest with you. I'm trying to remember. It's been a while since I've done assembly programming. I'll be doing a refresher myself when I put together the slides for it. But yeah, fortunately, do-while loops are pretty much the same as while loops. To be honest with you, I don't think I've ever actually used a do-while loop while in the wild. Wow, that's a terrible sentence to try to parse. Sorry, guys. I don't think I've ever used a do-while loop. They do the exact same thing as while loops. Just, like, it's not difficult to adjust a do-while loop into a while loop, and it's sort of somewhat easier to work with a somewhat smaller pool of constructs sometimes. Anyway, so that's a do-while loop. So let's talk about for loops. In this case, like, a for loop in C is a very different thing than a for loop in Python. They are very, very, very different. So don't imagine that the for loop that you're used to using in Python exists. Like, that type of thing doesn't even exist in C. Just a refresher, in Python, a for loop is used to iterate over the elements of a data structure. So if you have a dictionary that has, like, umpteen gazillion entries in it, a for loop will trace you through every single one of those dictionary entries. In C, for loops are just syntactic sugar for the most common loop structure. Notice before we had an initializer, a body statement, an update statement, and a condition. In C, a for loop puts the initializer, the condition, and the update all inside of the braces up front here. So in an actual example, if you wanted to do a countdown from 10, you would do int I is equal to 10, I is less than or equal to 0, I minus minus, and that is what a for loop looks like in C. It's a very, very different thing from in Python. Another thing that you guys are definitely going to miss that you had in Python was in, the in statement. There is no equivalent operation of inside of C unless you start digging around in libraries for functions that do that sort of thing. But it's not like functions that do that sort of thing don't exist. It's just you're going to have to find them. Like a search, you don't get to bind a search function to 2 characters in C. It just doesn't happen. But there we go. Let's take a look at what we are here. So I minus minus means decrement. That I is equal to I minus 1. So we've got like one more slide, but we are done for today, I think. And we'll pick up these the last 2 slides of this presentation on Tuesday. Thank you very much, folks, for the time and attention. This has been another lecture. Cool. I'll stay on a little bit to see if there's any questions. No, the reduction of I by one is the update to I. There you go. No, I'm pretty sure that it won't repeat. Well, it might. It might go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, which would be 11 times. Yes, I minus minus is the same as I equals I minus 1. Oh, good. I'm glad I got the pacing good today. There we go. Good. Take her easy, folks. Have a good weekend.